In today's lecture, we are going to look at a certain type of amplifier called the cascode amplifier. So, we will start off by looking at the common source amplifier that we have seen before. So, let us assume that the common source amplifier is biased with a drain current of I naught. It has an appropriate gate bias voltage, I will call that VB, and along with this I will also apply a small signal voltage Vs. We know that the output voltage that is taken at the drain for the amplifier is equal to minus Gm RDS times Vs. So, the gain of the common source amplifier is negative and it has a gain in for this particular circuit of minus Gm RDS, because I am using an ideal current source as the load for the transistor. In other words, there is no load resistance for this particular circuit. This minus Gm RDS is called the intrinsic gain of the common source amplifier of the MOSFET. So, this intrinsic gain of the MOSFET is the largest gain you can get from a MOSFET circuit with one single MOSFET, with one single device. Now, let us say we want even more gain from the amplifier. There are of course several different ways of doing this. One way to do this is to cascade two common source amplifiers. So, the output of the first common source amplifier is fed to the input of the second common source amplifier. I am not showing the biasing details in this particular figure. So, let the output of the first stage be VO1 and the output of the second stage be VO2. We know that VO1 is minus Gm RDS times Vs. This is the gain of the first stage, and VO2 is minus Gm RDS times VO1 or Gm RDS squared times Vs. So, the gain of this cascaded circuit is approximately the squared of the intrinsic gain of a single transistor. Now, you can see that this particular circuit consumes a power of, let us say these two transistors were biased at a current I naught and the supply voltage was VDD. The DC power consumed by the circuit is 2 I naught VDD. So, 2 I naught VDD is the DC power consumed, because the original circuit consumed a power of I naught times VDD. Now, suppose I want to get a gain of Gm RDS the whole squared, but I do not want to use twice the DC power. We need to come up with a different circuit that is capable of doing this. So, to see this, we will look at how the signal flows through the circuit. As you can see, in the original common source amplifier, when the source voltage is applied to the gate of the transistor, this causes a current of Gm times Vs to flow downwards from the drain to the source inside the transistor. And what happens to the signal current? If you had a load resistance, the signal current would probably flow through the load resistance, but in our case we do not have a load resistance because this is an ideal current source of value I naught. The only path for the current to flow through is the intrinsic drain source resistance of the MOSFET. So, this current flows through the RDS of the transistor. I will show that here. So, the total impedance at the output node is simply RDS, and therefore, this generates a negative minus GM RDS voltage, minus GM RDS times Vs voltage at the output node. Now, as you can see, there are, since the voltage gain is minus GM RDS times Vs, there are only two ways to change the gain of the circuit. One way is to change the GM, so we want to increase GM, or you want to increase RDS. How do you increase GM? You increase GM by increasing I naught, that is the bias current, and or increasing the size of the transistor, the width to length ratio of the transistor. These are the only two ways by which you can increase the GM of the device. Now, if you want to, there is a certain limit, if you want to use the same power, you can keep increasing the width over length, but there is only so much beyond which the device will not respond to increase in width. These are due to certain second order effects which we are not interested in right now. But the thing I want to point out is that the increase in GM with I naught and width is limited. So, eventually I need to start increasing RDS. How do you increase RDS? I increase RDS by choosing a longer length for the device. If I choose a longer length, then the RDS will get larger, but again, just like GM, if I keep increasing the length of the device, eventually RDS will reach, you will reach a point where RDS will not respond to any increase in length anymore. So, let us say that will be the maximum intrinsic gain of this device. We will assume you have already reached that maximum intrinsic gain. So, next you will, now that you have reached certain device limits, we will have to look at circuit techniques to increase this, increase the gain. Now, we will look at a circuit technique to increase RDS. So, we have seen in the context of current mirrors that the cascode current mirror tries to increase the output resistance of the circuit of the current mirror by stacking two devices on top of each other. In other words, if you look at the output resistance of this circuit, this is called a cascode connection as we have seen before. The output resistance of this circuit is, let me call these devices M1 and M2. The output resistance of this circuit is GM2 RDS2 times RDS1. It can be shown that this is the output resistance. In other words, the output resistance of M1 gets amplified by the intrinsic gain of M2. So, now this is one way to increase the output resistance of the circuit. So, let us see what a cascode amplifier will look like. If I were to build a cascode amplifier, I have a single current source I naught. I will again call these devices M1 and M2, and I am going to apply a bias voltage VB1, an appropriate bias voltage VB1 plus the signal at the gate of M1. Now, in the cascode connection, the gate of M2 is not connected to a signal, but is connected to an appropriate bias voltage VB2. We will in a few minutes we will see what is the appropriate value of VB2 we will want to use here. But let us look at the output resistance of this circuit. As we have seen, the output resistance of this circuit is nothing but GM2 RDS2 times RDS1. This is the output resistance of this circuit. Now, what happens to the signal current? The signal current generated inside M1 is GM1 times Vs, and as it turns out, this current also flows through M2 and eventually, since you are in this case we are loading it with an ideal current source, this signal current has no other path to flow through but the output resistance of this cascode circuit itself. Therefore, the output voltage at the drain of M2, so VO is GM1 Vs times R out with a negative sign. So, therefore, VO by Vs is minus GM1 times R out, which is as you can see, I will rearrange this. As you can see, this is the same as the intrinsic product of the two intrinsic gains that we wanted to achieve. So, now we have managed to create a gain that is the square of the intrinsic gain of a single device. So, in other words, if GM1, if the two transistors were identical, then GM1 and GM2 would be equal and RDS1 and RDS2 would be equal. So, we have managed to create a gain that is the square of the intrinsic gain. The difference in this case is that we have used only one single device, one single current I naught. So, the total DC power consumption is I naught times VDD. We do not need a cascade of two amplifiers. We have managed to do that, get this such a large gain with only one single amplifier. Now, it turns out that there are a couple of other variants of this circuit. So, as you can see, maybe I will go back to the previous circuit. You can see that the second device is a common, what is called a common gate device. M2 looks like this. If I were to redraw it slightly differently, this is device M2. The input for device M2 is basically the signal current of value Gm times Gm times Vs, and that is this current source represents device M1 that creates Gm times Vs current. For small signals, the gate of M2 is grounded, and if you have a load resistance, for example, at the output, the small signal current would flow through that load resistance. If not, it would flow through the output resistance of the circuit itself. So, therefore, as you can see, M2 is simply a common gate amplifier. So, in other words, the cascode connection is simply a common source amplifier stacked with a common gate amplifier. So, M2 acts as a common gate amplifier. Now, you can see that we have used M2 as an NMOS transistor. In reality, M2 need not have the same size, so it could have a different GM and a different RDS, and that would be a design parameter of interest. But first, let us look at the constraint on VB2. Because it is a common gate amplifier, the gate voltage VB2 has certain constraints. So, if you look at VB2, I want to find out what is the maximum value and the minimum value of VB2 that can be applied to this circuit. So, to do that, I am going to denote the voltage at the intermediate point as VD1, which is the drain voltage of M1. I am looking now only at bias quantities. So, VB2 is nothing but VD1 plus VGS2. In other words, I am applying KVL around that loop. So, what does that mean? If I change VB2, the value of VB2, since M2 has a constant current I naught set by the current source on top, what will happen is that VGS2 will remain constant as long as M2 is in saturation. If that happens, VD1 will follow VB2 with a difference of VGS2, which is set by I naught. So, VGS2 is calculated at a bias current of I naught. So, if I keep decreasing VB2, what will happen is that if VB2 decreases, VD1 will continue to decrease. Note that for transistor M1, this node is at a constant voltage and the gate voltage is constant, the drain voltage is dropping. Therefore, the transistor will eventually move towards will start moving towards the triode region. Eventually, it will hit the edge of the triode region, beyond which we do not want to move. Therefore, the absolute minimum voltage possible will clearly happen when VD1 is equal to VD sat of M1 plus VGS2. If I were to calculate this is nothing but root of 2 I naught mu over mu n Cox W over L of M1 plus VGS2, which is nothing but VT2 plus VDS sat of 2, which is 2 I naught over mu n Cox W over L of 2. This is the minimum value that VB2 can occupy. What about VB2 maximum? Now, let us assume that I am increasing the voltage VB2. I will show that in red. If I start increasing VB2, you can see that again VD1 will start increasing. So, therefore, M1 is moving further away from triode. So, there is no problem with M1, but note that at the output, if the output were biased at some voltage VO, eventually that was set maybe through feedback, eventually the transistor M2 will go into the triode region. That will happen when you hit the triode condition for M2, and that is simply given by this VB2 max minus VT equals VODC. So, in other words, VODC is the drain voltage and that becomes exactly equal to the gate voltage, which is VB2 minus VT, and therefore, VB2 max is nothing but VT2 plus the output DC voltage. So, this as long as you choose the bias voltage VB2 such that it lies between these two values, you will ensure that for DC both transistors are in saturation. Now, if you remember, we had said that the cascode is a common source amplifier cascaded with a common gate amplifier. The common source amplifier is an NMOS common source amplifier, and in the first case we had seen that the common gate amplifier is also an NMOS device. But remember that the NMOS and PMOS, both NMOS and PMOS transistors have the same small signal equivalent circuit. Therefore, in reality either of these two devices could be NMOS or PMOS, because only the biasing details will differ. Let us look at one variant where the common source amplifier is composed of an NMOS device, but the common gate amplifier is composed of a PMOS device. So, the common source amplifier has a bias voltage VB plus the small signal voltage Vs applied at its gate, and now you are going to have a common gate amplifier, but instead of an NMOS transistor you are going to have a PMOS transistor. Now, because the biasing details will change, I am going to show it in a draw the circuit in a slightly different fashion. I am going to draw it like this. In a minute you will see why. I am going to connect the gate of PMOS transistor M2 to some bias voltage VB2. Now, why am I drawing the PMOS transistor like this? Because in general convention current flows from, bias current or total current flows from top to bottom, and inside the PMOS transistor current will flow only from the source to the drain, which is the opposite of the NMOS device. Now, to bias the NMOS and PMOS device, remember that at the output we connected a current source. In this case we will have a current source to ground, I will call that I2, but clearly you need a current flowing into the drain of NMOS transistor, and I will show that as a current source I1. What is the bias current, drain current of M2? That is simply I2. The bias current of M1 is clearly I1 minus I2. So, the NMOS transistor is biased at a current I1 minus I2, and therefore, VB1, the bias voltage for the NMOS device, should be chosen appropriately. In such a case, if you look at the small signal equivalent circuit, I will show that in blue. The gate of the PMOS transistor will be grounded. So, this acts as a common gate amplifier. This clearly still acts as a common source amplifier, and this is an open circuit and this is an open circuit, and therefore, the circuit still looks like a common source amplifier stacked with a common gate amplifier, and the overall output resistance is still GM2 RDS2 times RDS1. The overall transconductance, in other words the signal current flowing, is GM1 times Vs. The overall gain seen from the output, which is taken at the drain of M2. So, the overall gain of the circuit is still minus GM1 RDS1 times GM2 RDS2. So, it still looks like the product of two intrinsic gains, the only difference being that one of the devices is an NMOS, is a PMOS transistor. This particular circuit is called a folded cascode amplifier. Because the circuit looks like, because the way the circuit is drawn, the current is folded into the PMOS device. And you can see, I will leave this as a homework exercise. I will leave the calculation of VB2 max and VB2 min as an exercise for the viewer. Now, we will complete with a small discussion on how to increase the gain further. Suppose I want to increase the gain even further without increasing the number of stages, there is one more option to do this. I will show that with an illustration on the NMOS cascode. Now, in the original cascode amplifier, the gate of M2 was connected to signal ground, it was connected to an appropriate DC voltage. In our case, what we will do is we will try feeding back the signal from the drain of M1 to the gate of M2 through an amplifier of gain minus A. As you can see, you need an amplifier of minus A to ensure that you have negative feedback. As it turns out, this particular circuit has an R out which is equal to A times GM2 RDS2 times RDS1. In other words, the negative feedback boosts the output gain, output resistance even further by an value equal to A. What does this mean for the gain of the circuit? This means that VO over Vs, which is the gain of the circuit, is now minus GM1 RDS1 into GM2 RDS2 into A. So, in other words, if you have an amplifier of gain A, which may also be a third intrinsic gain, you can get gains of the order of the cube of GM RDS. If A were of the order of an intrinsic gain, VO by Vs is of the order of GM RDS the whole cubed. This particular circuit is called the gain boosted cascode.